Now for example 2, we're going to look at variable force, and in this case, this one's linear. This is kind of our easiest example of variable force, the linear example. And I showed you the cable that I had from the hanging from the chair, and that cable weight I said was 20 pounds, and then again the chair height, I'm going to say that that is 4 feet. And I showed you how as I lift the cable, the weight will change. So if like I showed you, if I lifted the cable halfway up, now I only have 10 pounds left to lift, and thus we have a varying weight, so we can call this our variable force. So at 4 feet, the weight is 20 pounds, right, as it's hanging 4 feet. To move it 1 foot up, because our weight takes into account gravity, to move it 1 foot up is, if we have our work formula, work equals our force, which is the 20 pounds, times the 1 foot, and so we get 20 foot-pound. But then once we lifted it 1 foot, we're now at 3 feet. And if we think of this proportionally, then the weight is now 15 pounds. And to move that 15 pounds 1 foot, that's going to be our work equals 15 pounds times 1 foot. And we get the 15 foot-pound. So I went ahead and just finished off, okay, at 2 feet, the weight is now 10 pounds. I'm moving it a foot, so my work is 10 foot-pound. At 1 foot, the weight is now only 5 pounds. That cable is really short now, so it only weighs 5 pounds. And the work, thus, if we move it 1 foot, is now 5 foot-pounds. And so I want to represent this graphically. So looking at my graph, again, I have force on the y-axis and distance or displacement on the x-axis. And I said at 4 feet hanging, the weight was 20 pounds. So I could graph the point 4, 20. And at 3 feet, it was 15 pounds. So I'm going to graph the point 3, 15. At 2, it was 10 pounds. So 2, 10, and 1, 5 to represent all those points that I found. So this total work would be the area under this curve, but I only looked at subintervals of 1 foot. So if I were to draw a rectangle going across where my right endpoint is at 4, 20, and then I have this rectangle with the height of 20, but it only has a width of 1 from 3 to 4, then that rectangle there, that would actually have a work of 1 times 20, so that would be 20. Oops, that doesn't look good. So can't really see that 20, so let's mark that again. So, ooh, no. I should edit this out, but 20. So that's the total work for that rectangle. And then I'm going to do the same thing, draw a rectangle up 15, ending at 3, so it goes from 2 to 3, and that has an area of 15, because 1 times 15. And then I'm going to also draw a rectangle from 1 to 2 up to 10. That has an area of 10. And then from 0 to 1 up to 5, that has an area of 5. So now if I look at the total work of this, this would be total work equals 5 plus 10 plus 15 plus 20, which is, what, 15 plus 15 is 30. So 50 foot-pound. And if we scroll up to what we were working with earlier with constant force, we got 80 foot-pound, which makes sense because the weight stayed 20 pounds the entire way up, whereas this one actually gets less, so it makes sense that we have a little less. Now this is just an approximation of this problem because we did subintervals of 1 foot. What if instead I took this graphically and said, let's look at the work at, say, half a foot and 1 foot and 1.5 feet and 2 feet. What if we looked at it in terms of subintervals of 0.1, a tenth of a foot, and 2/10 of a foot? So these rectangles could get smaller, 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 smaller. But we have a linear relationship here. So this is a linear function. So I can represent this graphically as a line. And I'm going to go ahead and sketch it again. I don't like putting too much on a single graph. So we're going to have the same graph, but now up here I have 20, over here I have 4, and then I have 0, 0. So I have a line going from 0, 0 to 4, 20. And so this area now is what I want to find. This triangular area. And I could find this triangular area just using geometry, but we're going to look at this in terms of our Riemann sums and integrals to give us an idea of how to work with calculus with this. So this total area, this would be the accurate work calculation for this variable work problem. If we were to take a slice of this problem here, so let's take a, some kind of subinterval, and we'll just take this rectangular slice in the middle here. It's going to have a width of delta x. That's going to be our subinterval width. And then the height, we have to see what that's represented by, and that would be represented by the function. And so the function here, you can work it out on your own, but this function here of this line is actually y equals 5x. So you could find that on your own, but that's what the function is. So if we do our Riemann sum from I to n, we have our function would be 5x sub I star times our delta x. So our Riemann sum, what we're doing is we're taking our force, that's our y value there, times our distance, which is that delta x, at that kind of ith spot, that slice. And then we're adding up all of those slices, just like we did with, as we've been doing with integrals, and we could use that Riemann sum. So now let's look at what the actual would look like if we use the limiting process and we got the integral. Now the integral is going to go from 0 to 4, right? And we have 5x dx. Solving this, we get 5x squared over 2, evaluated at 4, at limits 0 to 4. And this would be 5 times 16 over 2. That 16 divides into 2 makes 8. We get 40 foot-pound. Now notice that 40 foot-pound is slightly less than our 50 foot-pound, which that does make sense, because if we were to lightly sketch all the rectangles on here, those were right endpoints. And so notice the rectangles were an overestimate of the problem. So the 40 foot-pound makes sense, and that would be our variable force. To wrap up the two examples and show how integration can be used on any of this as long as you have your function, we have our constant force. When we looked at that graphically, that was a constant function of y equals 20. So the integral that we could write for this problem would have been 0 to 4, 20 dx, and that's going to be equal to 20 times x with the limits of, they evaluated at 4 and 0, so 20 times 4 minus 0, we get the 80 foot-pound, which is what we got in the original example 1. And so you can also do this just by finding the area of the rectangle, 4 times 20. You don't have to use integration, but I wanted to show how that still works. And then, of course, here's the variable force linear problem we just did with the y equals 5x as the function. So we have the integral from 0 to 4, 5x dx. And when we solve that, as we did before, we get the 40 foot-pound. So I wanted to make sure that you saw that these can both be done using integration, though, especially for the first example, you do not have to use integration, but you could.